This is the third lecture in Chapter 2 and the final lecture of the unit. Today we'll learn about matter and energy. Matter is anything that has mass and takes up space. Matter is made up of either atoms or compounds. Important elements in this class include hydrogen, carbon, oxygen, nitrogen, phosphorus, sulfur, chlorine, fluorine, bromine, sodium, calcium, lead, mercury, arsenic, and uranium. Parts of an atom. The proton and the neutron, both of those are found in the nucleus. The proton is a positively charged particle and the neutron is a neutrally charged particle. Electrons orbit the nucleus, that is, they orbit the protons and neutrons. They are negatively charged. They are responsible for bonding to hold compounds together. The number of protons in an atom is the atomic number from the periodic table. Atoms will have the same number of protons and electrons. The mass number is the total number of protons and neutrons. Electrons have such a tiny mass that they don't count. Isotopes have the same number of protons but a different number of neutrons. For example, H3 tritium, that's a hydrogen atom with one proton and two neutrons. The normal hydrogen has one proton. Chemical formulas. Chemical formulas are a shorthand writing of compounds or molecules. Example, NaCl stands for sodium chloride or table salt. H2O stands for water. Those are both chemical formulas. Some nonmetals bond with themselves in gas form. O2, N2, and O3 being oxygen gas, nitrogen gas, and ozone. Organic molecules versus inorganic molecules. Organic molecules are carbon-based. Hydrocarbon molecules with hydrogen and carbon, for example CH4, which is methane. There are chlorinated hydrocarbons that have hydrogen, chlorine, and carbon. DDT is an example, which is a pesticide that's now banned in the United States. And then there are simple carbohydrates, which have carbon, hydrogen, and oxygen. Glucose is an example. The following are not organic molecules: sodium chloride, water, carbon monoxide, and carbon dioxide. Matter has quality. High quality matter is useful, concentrated near the surface of the earth, high potential for a natural resource. Low quality matter, on the other hand, is dilute, it's hard to find, and has very low potential. Examples: aluminum ore is low quality, while recycling aluminum cans is high quality. Why? Because aluminum is hard to find, has low potential, it's dilute, whereas recycling aluminum is concentrated and easy to find as a resource. Another example, solid salt in a salt mine is high quality, while the salt in the ocean is low quality. Why is that? Because solid salt is concentrated near the surface of the earth. It's a resource that's easy to get to. Whereas in the ocean, it's diluted and hard to extract from the ocean. Okay, what state are you in? Solid, liquid, gas, or plasma? Solid, molecules are tightly packed, will hold its shape on its own. A liquid, molecules are tightly packed but still able to flow around each other, holds shape of container. Gas, molecules are loosely packed and will fill a container. And plasma has very high energy. Electrons are removed, found in stars and lightning bolts, and it can be made. There's plasma TVs and plasma fluorescent lights. Okay, let's talk about energy. Kinetic energy and potential energy. I know you have all learned about this before. Kinetic energy is the energy of motion. Examples are wind, heat, electricity. Potential energy is stored energy, and it's available for use later. Examples are an unlit match, a roller coaster at the top of the hill, and energy in gasoline. Energy in the form of waves is called electromagnetic radiation. This is the electromagnetic spectrum that you see at the bottom of the page. It shows the different types of electromagnetic radiation and the energy. The electromagnetic radiation that we see is called visible light. It's about in the middle of that bar graph. On the left-hand side, you see gamma rays. On the right-hand side, TV and radio waves. Gamma rays have very high energy. TV and radio waves have very low energy because they have longer wavelengths. The gamma rays have shorter wavelengths. You can see they're all squished together there at the end, and therefore have very high energy and are capable of more damage to living things on Earth. Heat transfer. Temperature is the measure of the movement of molecules and atoms in a substance. Convection is the rise and fall of heat. Conduction is heat transferred by direct contact with a heat source. In radiation, heat can transfer through air or space. All right, radioactivity, what is it? The nucleus throws off particles, the nucleus of an atom throws off particles in order to become stable. Half-life describes how long it will take for 1/2 of the amount of material to turn into a different isotope. This allows for dating of ancient material, carbon dating. Dangerous radioactive materials take 10 half-lives to become safe, and nothing can change the half-life time, not temperature, pressure, etc. Nothing can change that half-life. Here are some example half-life problems. You will do some of these tomorrow. Let's say plutonium, which is a radioactive substance, plutonium-239, has a half-life of 24,000 years. How long must it be stored before it will be safe? Remember from our last slide that it takes 10 half-lives for a radioactive substance to become safe? So you take the half-life, 24,000 years, multiplied by 10, that's 240,000 years. Iodine-131 has a half-life of 8 days. After 4 half-lives, what fraction of the sample is still radioactive? Well, you think about it this way. You start with a whole, and then half of it undergoes radioactive decay. Half of the iodine-131 is left. And then another half-life occurs. You cut the remaining iodine-131 in half, and you end up with a quarter of the original iodine-131 left. You do that through 4 half-lives, and you end up with 1/16 of the original iodine-131 left. In the next example, you'll see how many half-lives and what fraction of the original sample will be left after that many half-lives. More half-life problems. Let's say a bone is found to have only 1/128th of its carbon-14 remaining. The half-life of carbon-14 is 5,370 years. How old is the bone? Well, we determined in the last slide that 1/128th of a substance remaining, of an original substance remaining, takes 7 half-lives. So we would take 5,370 and multiply that by 7, and that gives us 37,590 years. Another example, uranium-235 has a half-life of 710 million years. If the sample is considered safe when it is at 10% of the original, how many years would that take? Remember that it takes 10 half-lives for a radioactive substance to become safe. So we take that 710 million years, multiply by 10, that gives us 7.1 billion years. In scientific notation, that's 7.1 times 10 to the 9th years. Nuclear fission. A large unstable nucleus splits in two. This is fission. This releases energy and it releases neutrons. The neutrons will make other unstable nuclei split. It starts a chain reaction of releasing energy from the splitting of the atom. You must have a critical mass, that means enough material for a chain reaction to take place. Nuclear power plants capture the energy from fission and utilize it to make electricity. Here's a diagram showing the nuclear fission. We have uranium-235. It's hit with a neutron, splitting the atom, releasing energy. It also releases neutrons, more neutrons that go to hit more nuclei of uranium-235, and those split, releasing even more neutrons. So more and more energy is released with each step of the chain reaction. Nuclear fusion is much more difficult on Earth. Stars use this. You get a lot more power from fusion than you do from fission. Nuclear fusion combines two smaller nuclei into one nucleus, so it's the combining rather than the splitting of atomic nuclei. Power from the combination of hydrogen into helium, that's a hydrogen bomb. DT fusion is deuterium, that's hydrogen 2, with tritium, hydrogen 3, to make helium and one neutron. That's another example. And DD is 2 deuterium to make helium and one neutron. An example of frontier science that we talked about earlier in this chapter is using the DT fusion for power. That may not be ready for several years down the road. Unbreakable laws. No matter how hard you try, you can't break these laws. The law of conservation of matter means you cannot create or destroy matter. It can only change form. This is shown in chemical equations by balancing the equations. You can see a balanced and unbalanced equation here. 2 hydrogen, 2 oxygen, going to 2 hydrogen, 1 oxygen. That's not balanced. That's not the conservation of matter. If we start with 2 hydrogens and 2 oxygens, we have to end with 2 hydrogens and 2 oxygens. They may be recombined, but the matter must be conserved. If we have 2 hydrogen atoms plus 1 oxygen atom, and we get 2 water molecules, that is balanced because we end up having 4 hydrogens and 2 oxygen atoms at the beginning of the reaction and at the end of the reaction. Try to balance this one. In environmental science, what the law of conservation of matter tells us is that there is no away. Earth is a closed system. We don't get any new materials in. We can't get rid of the waste that we produce. The severity of a pollutant is based on the chemical nature of the pollutant, what it's made of, the persistence, meaning how long does it stay in the environment, the concentration of it, the chemical nature being acidic, basic, molecular makeup, for example, CFCs that hurt the ozone, and the concentration is usually measured in parts per million, parts per billion, or parts per trillion.
Good morning.
Persistence. Degradable or non-persistent. This type of substance will break down by chemical, physiological, or biological means. For example, roadkill. So it won't persist very long. A degradable material won't last long. Biodegradable can be broken down by completely natural processes, usually by bacteria. If you throw out a banana peel onto the ground or an apple core, that will biodegrade by bacteria and completely return to the earth through natural processes. Then there are slowly degradable or persistent items. They take over 10 years to decompose. The harmful pesticide DDT is an example of this, and we'll talk more about DDT not too long from now. And then there are non-degradable or persistent items in the environment. They cannot be broken down. Mercury, lead, arsenic are examples of non-degradable and persistent chemicals. The laws of thermodynamics. The first law of thermodynamics is that in a chemical reaction, we cannot create or destroy energy, only change it. You can't get something for nothing. So the first law of thermodynamics is like the conservation of matter. Energy can't be created or destroyed, it only changes form. The second law of thermodynamics states when energy changes form, some useful energy is always degraded into less useful energy. You'll never break even.